All right, section 6.4. We are flipping back in our notes packet. All right, back to where we had left off earlier. 6.4 deals with rational exponents. Rational meaning what? A fraction, okay? So we're dealing with exponents that are now fractions. So I want you to do a little review. What do we do when we have a base to a power times the same base to a power? We add the powers, okay? What do we do when we have a base to a power divided by the same base to a power? We subtract it. If we now think of having those be fraction powers, if we're going to be adding and subtracting, we're going to need what? How do you add and subtract fractions? What do you need? Common denominators. So we're going to have to do some converting to get common denominators. What do we do when we have a base to a power to another power? We multiply them. Do we need common denominators to multiply? No. Okay, so we are going to be looking at simplifying expressions that have these rational exponents. As I said, we're going to take a couple days to work through all of this. In general, we can take a radical expression and convert it into a rational exponent. Okay, I'm going to say that again. We can take a radical expression. So when you saw that radical symbol, a square root symbol, a cube root symbol, that type of thing, we can convert it and make it a fraction power, rational exponent. If we are taking the nth root of x, we can rewrite that as x to the 1 over n, the 1/nth power. Okay? So if I want to take the square root of 36, I can rewrite that as 36 to the 1/2. Whatever your index is here becomes the denominator of your fraction. So a cube root would become a 1/3 power. A fourth root would become a 1/4 power. Does that make sense? Okay. So how do we simplify when they're in that form? If it helps you to convert it back into a radical notation, you can. In general, whatever form the question was given to you in is the form we want the answer, unless they specifically are asking you to convert it. Okay? So for this one, we are simplifying 216 to the 1/3 power. If it helps, think of it as the cube root of 216. You can use your power charts. What is the cube root of 216? Okay. For the next one, what does it mean to take 7 to the 1/2 power? A 1/2 means what kind of root? Square root. So one way to look at this is to say I'm taking the square root of 7 times the square root of 7. Well, that becomes the square root of 49, which is just 7. Is there another way I could have looked at that question? What could I do?
You can multiply the fractions.
Multiply them or add them? Add them. I could have just looked at this and said, I have a base to a power. I have the same exact base to a power. I can add the powers. What's 1/2 plus 1/2? 1. And what I got here was 7 to the first power. Does that make sense? So either way of looking at it is fine. How about this next one? The bases aren't the same. But let's think of them in radical form. They are both being raised to a 1/4 power. So I have the 4th root of 5, and I'm multiplying it to the 4th root of 125. Since they're both 4th roots, could we multiply those back together and put it all under a single 4th root? Okay, we did that in the previous half of this chapter. What is what is 5 times 125? And what is the 4th root of 625? Okay. Questions on any of those three? All right, I'm going to pause the recording. I want you guys to try the next three. All right, let's check these. What does 64 to the 1/2 power mean? We're square rooting 64, so our answer would be 8. One thing to remember, when we talked about square roots and even roots needing a plus minus, If you have something like this where it's 64 to the 1/2, they are implying the positive or the principal root. Okay, they would put a plus minus in front of it if they wanted both. Okay, next one, 11 to the 1/2 times 11 to the 1/2. We could add the powers, right? Same base. Add the powers, that would be 11 to the first, or just 11. Again, if you want to think of it as the square root of 11 times the square root of 11, you're still going to get the same answer. All right, next one. Different bases, but they have the same kind of power. Yes? So you can combine things if the bases match. You can combine things if the powers are the same. So this is a square root of 3 times the square root of 12, which turns into the square root of 36, which is 6. Questions so far? Okay. The ones that we've looked at so far have had a numerator that is just a 1, right? We had a 1/2, 1/3, 1/4. That's what this first part is talking about, okay? But what if the fraction power has a numerator other than 1? If we have a to the m over n power, we know that the n describes the type of root that we're supposed to take, square root, cube root, fourth root, etc. The top number is your power. So we can rewrite this in two different ways. We could say, I'm going to take a to the mth power first, and then take its nth root. Or we can take the nth root of it first, and then raise it to the power. Both options get you the same answer. Doesn't matter to me at all which way you go. However, the one thing to think about, when you take a number to a root first, when you take its root, you have a number that you're making smaller, correct? When you take its root, it gets to a smaller number. Then you can take that smaller number and raise it to a power. If you do the power first, you're taking a number, making it big, and then you're trying to take that big number and use some kind of root on it. All right? Now, if you have your power chart handy, that's fine. Either way, it'll get you the same thing. But if you're trying to do it by hand, it's usually easier to take the root first and then raise it to a power. We have a statement here. If m is negative, then a cannot equal 0. Why would that be the case? What happens when we were taking something to a negative exponent? What did we have to do? We had to flip it, right? We had to do its reciprocal. Well, what happens if you take an a value, flip it over? If a is 0, can't do it, right? We can't have 0 as our denominator. Okay. Got a little picture here to help you remember the order. Your top number is going to be your power. Think of the sun as solar power. Right? Sun's up in the sky, it's on the top. Okay? Solar power, power's on the top. The roots of a tree are on the bottom. So your bottom number, your denominator, is going to be the root. Okay? Top number is your power, bottom number is your root. Okay, so this question is saying, what are x to the 3/7 and y to the negative 3.5 in radical form? We're not simplifying it. We're not getting a number answer. We're just converting it to its opposite notation. Okay, so right now it's as a rational exponent in rational form, in exponential form. We want to write it in radical form. So looking at x to the 3/7, the top number is our power, and the bottom number is our root. So we would rewrite this and say we are taking the 7th root of x to the 3rd power. Now again, you can write that either way. That would be equivalent. One shows you taking the root first, one shows you taking the power first. Okay? What if our power is negative 3.5? What would that be as a fraction? 3.5. 7/2. Okay, so let's think of this as y to the negative 7/2 The 2 on the bottom means we are doing what? We're square rooting. The 7 on the top means we're raising it to a 7th power. And the negative means what? Negative means we have to flip it. Okay, so we are taking the square root of y to a negative 7th power. We're going to flip it over. And we have the 7th power of y, and then we're square rooting it. It's all a denominator. In the past, we've said you can't leave radicals in the denominator. What would we need to do to rationalize that? We need to multiply by what? We're doing square roots, right? So we need a square root of something. We have 7 y's, right? We need groups of 2. So how many more do we need to make even groups? 1 more. So we're going to end up with the square root of y over the square root of y to the 8th. Yes? Which becomes what? Y to the 4th. Now, when we simplified these things in the first half of the chapter, you didn't know about fraction powers. So I want you to think of this. We said we're square rooting y to the 8th. So we had 8 objects. We were taking them in groups of 2. If I rewrote this as a fraction exponent, it's really y to the 8 halves, right? And 8 divided by 2 is 4. Does that make sense? Okay. I'm going to pause the recording. I want you guys to try the next 2. Now you're going the reverse. Okay? I gave you the expression with a radical symbol. I want you to write it with a rational exponent. All right, so the square root of a to the 5th would be written as a to the 5 halves, right? 5th power square rooting. Okay, this would be b to the 3/5. Okay. Next question. It says, Kepler's third law of orbital motion shows how you can approximate the period p in Earth years that it takes a planet to complete 1 orbit around the sun. Use the function p equals d to the 3 halves. I know that's blurry on your paper, so rewrite it. P equals d to the 3 halves, where d is the distance from the planet to the sun in astronomical units. An astronomical unit is about 93 million miles, or relatively the distance from the Earth to the sun. How many Earth years does it take Mars to orbit the sun if Mars is 1.52 astronomical units from the sun? Okay, so we are given this equation, big long word problem with pretty basic formula. And they gave me a value of 1.52 astronomical units, okay, as my distance. What am I going to do with 1.52? Put it in for which variable? D, the distance. Okay, so P equals 1.52 to the 3 halves power. How would we type that on our calculator? Can you raise something to a fraction power in your calculator? That's what I want you to check. I'm going to pause the recording. You guys grab your calculators and try it. All right, so final answer here. P is about 1.87 what units would we put on here? What are we trying to find? Earth years, yep. All right, so it's going to take Mars about almost 2 of our years to orbit the sun. Does that make sense? Sure. Just an example of where you might see a rational exponent. Okay. The next thing in your notes is a quick chart that reviews all of those power rules, all of our rules for exponents. We talked briefly at the beginning of class a to the nth power times a to the nth power. If the bases are the same, we can add the exponents. The one thing we have to be careful of, if our exponents are now fractions, we have to make sure we have common denominators. That is true when we're adding. It is true when we are subtracting. All right, we need common denominators for those. We do not need common denominators to multiply or to distribute. Okay? It says, if the indices don't match, you can combine radical expressions if you first convert them to expressions with rational exponents. So thinking back to what we did in the first half of this chapter, if I had said take the 4th root of x and divide by the 8th root of x, you would have said I can't do it. They're not the same kind of index. Now we know that we can rewrite these with a fraction exponent. And we have ways to get common denominators with fractions. And if the denominators are the same, it means we're taking the same kind of root. So there is a way to simplify this. For this one, your first step is to rewrite them with fraction exponents. So the 4th root of x cubed could be written as x to the 3/4 power. Okay? The 8th root of x squared can be written as x to the 2/8. Now, we have an option. 2/8 can be reduced, yes? If we reduce 2/8 to 1/4, we now have a common denominator. If we hadn't been able to do that, we would have had to use some multiplication to get common denominators. So we have x to the 3/4 divided by x to the 1/4. When we have a base to a power in the numerator and the same base to a power in the denominator, what do? We subtract them. What's 3/4 minus 1/4? And 2/4 can be reduced to 1/2. Now, earlier I said, whatever form the question was given in should be the form you give your answer unless it's specifically asking for something else. So since it was given to me in radical notation here, I'm going to convert this to the square root of x and put it back in radical notation. Okay? All right, let's try one more. This next one is saying take the what? Square root of 3. How could I rewrite that? 3 to the 1/2? Yes? Okay. I've got the 4th root of 3. Can I write that as 3 to the 1/4 power? Okay. Bases are the same. They're both 3's. So I'd like to be able to put this together. In order to do that, I'm supposed to be adding the powers, but I cannot add them until I get common denominators. What could I do? I can convert 1/2 into 2/4. So I have 3 to the 2/4 times 3 to the 1/4. That means 3 to the 3/4, right? Adding the powers. It was given in radical notation, so I'm going to rewrite my answer that way. I am taking a 4th root of 3 cubed. Now for small numbers like that, you know what 3 cubed is, right? I'd have you go ahead and simplify that as to the 4th root of 27. If it's a huge number, then we would leave it in its exponent form. All right, I'm going to pause the video. I want you guys to try the next 2. All right, let's rewrite these in rational exponent form. So we have x to the 3/2 divided by x to the 2/3. What denominator would we get? 6. All right, so converting, we'd have x to what power? 3/2 is the same as 9/6, and 2/3 is the same as 4/6. We can now subtract our exponents. 9 minus 4 would be 5/6. It was given in radical form. We're going to rewrite it in radical form. What kind of root are we taking? A 6th root of x to the 5th power. Okay. Our last one here, the square root of 7 is 7 to the 1/2. We're multiplying to 7 to the 1/3. Okay, in order to put these 7s together, we have to do what? Common denominator, which would be 6. All right, so 1/2 is 3/6. 1/3 is 2. So we have 7 to the 5/6. So again, we're doing a 6th root of 7 to the 5th power. Now, that is a bigger number. Anybody look it up? Yep. Okay, I wouldn't expect you to know that by hand, right? So without a calculator or your power chart, you could have left it this way. Okay, all right, we'll do some more of that type tomorrow. For tonight, I want you to do page 386, numbers 10 through 38, 105 to 107, and 114 to 119.